Hello everyone, welcome to COMP251 Data Structure and Algorithms. In this video, I'm going to talk about abstract data type Q. In the previous, last session, we have talked about the abstract data type list. And this week, we are going to learn about two data structures, stack and queue. In this video, I'm going to focus on Q. So Q is, in fact, a special form of a list that you are restricting the operations. You are not going to allow all of the operations like adding and removing the data. Remember, the list actually allows you to add and remove the data at arbitrary positions, right? But in the queue, we are going to restrict these operations and just allow to add the data from one side of the list and remove the data from the other side. So these two sides are going to have different names. The sides that we are removing the data from is going to be called front, and the side that we are adding the data to is going to be called back or rear of the queue. Okay, a stack was also actually another a restricted form of a list that we add or remove from the we add or remove the data from the just one side of the list, and that side was going to be called the top of the stack. Okay, so based on this definition, the operations that we can define for the queue, so this is going to be the specification of the queue, is going to be two main methods for add or remove from the queue. Adding from the queue, we call it NQ. We are going to actually give it a specific name here. And the removing usually actually called DQ. Add is going to add the data from to the rear or back of the queue, and DQ is going to remove the data from the front side of the queue. You can actually add another operations very similar to the one that we have in a stack. We call it pick. This method is going to return, it's not going to change the data in the queue. It just actually tells us that what is in the front of the queue, what is the next item that can be removed. If you call the DQ, this item is going to be removed from the stack. So it's just like this is the next item which is accessible from the queue. You are not going to allow access to the indexes in the queue, right? This is not a list anymore. We can also add methods like size, is empty, clear, and these kind of general methods that we define for all abstract data types. So abstract data type Q, because you are adding from one side and removing from the other side of the list, is also actually called the first in, first out actually data structure. So the whole idea here is that the item which has been stored in the this abstract data type the most is going to be the first one which is going to be removed from the queue. So as the name tells you, the queue is going to help us to implement wherever in any application that I need a queue, the data structure queue is going to be useful. So if I wanted to graphically show you how does the queue, the abstract data type queue works, it's just like you have a list and you are actually keep track of the both sides of it. Where is front, which side is going to be, the other side is going to be called back, or sometimes we call it rear. So here in this lecture, I would use back and rear interchangeably. Both of them are going to be referring to the same concept here. Okay, so when you are enqueuing to queue, you are adding an item, right? So that item is going to be added to the end of the queue, and when you are removing an item, it's going to be called dequeuing an item, and This is just like you are removing the next item at the front of the queue, and so front is going to be updated and refer to the next item. Queue is one of the most common abstract data types in computer science. Stack and queue, both of them actually. They are very simple, but they have a wide variety of applications actually. So everywhere that you have, you need to implement a client-server model, you need a queue, because queue is going to help you to implement the first in, first out policy. So assume that you are implementing a client server model, and on the server side, you are receiving queries from different clients, right? So how you are going to serve those queries, where you are going to store them, and in which manner you are going to serve them. So having a queue is going to help you to implement the first in, first out policy. The one who has been waiting in the list for the most is going to be the one who is going to be served first. So basically most of shared computer services like the web, file, FTP databases, different databases, mailboxes, printers, all of them kind of are using some form of a queue. So for example, in a CPU, the jobs assigning different actually threads are going to be implemented using a queue. Many graph algorithms, like the birth first traversal in trees or birth first search in general graphs, will be implemented using a queue. So there are many applications for queue, although this data structure is very simple. Before we are going to actually to the implementation, discuss the implementation for the queue, I need to mention that just like in the list or in the stack that we talk about different special cases, we need to think about them here as well. That what would happen if someone called dequeue, removing an item from an empty queue. So in this case, we would expect that if there is nothing in the queue, nothing can be actually removed from the queue. So in this case, we would throw an exception. So we consider this in our implementation. We are going to throw an exception if the queue is called over an empty queue, or even for the method pick that check what is the next item on the front of the queue. If the queue is empty, so in this case, it's also going to be an exception, right? Let me actually just jump into the implementation. Just like a stack and list, because queue is a specific form of a list, I'm going to discuss two different ways to implement the abstract data type queue. The first one of them is based on array, and the other one is based on linked list. Here I'm going to actually discuss that. First, I'm going to discuss it over the linked list, because it's just slightly easier than when we are actually implementing queue using an array. And then I'm actually just going to discuss the array-based implementation. Exactly like a stack, our goal here is that to get the most efficient time complexity for all the operators. So all operators like enqueue, dequeue, and pick, our goal is to implement them in constant time. So let's see that how we can reach to this goal. So the first implementation for queue is using linked list as the core data structure. So we have here two things to actually choose to decide about them. In the stack, we just had one side of the stack which was important for us, right? We would think of it as, okay, a stack is a list that I just care about one side of it, so I need a pointer to one side of it, right? That was the top of the stack. But in the queue, I need to actually choose two different actually pointers, one front and the other one is rear. So when I'm thinking about using using a linked list as the core data structure, I should choose that which side is going to be the front and which side is going to be the rear. Remember when we discussed about the linked list, we had a version of a linked list that we keep two references, one reference to the head, to the beginning of the linked list, and the other reference was tail, that actually referred to the last item. So here it's actually just kind of some head is going to be called front or rear, and tail is going to be the other side, right? So this is just the choice that which one is going to be head and which one is going to be front and which one is going to be tail. So, but just reviewing the time complexity table for different methods, remember we had actually this table for the linked list, accessing to the front, removing from the, accessing to the beginning side, removing from the beginning side, adding to the beginning side, and all of these actions to the other side, to the end of the linked list. So this table shows the time complexity for the case that we have a single linked list and we have kept both references for head and tail. So you can actually see that removing and adding and access to the data to the front of to the head is going to be done in constant, right? When you are actually removing or adding an item to the beginning of a linked list, for example, when you are adding something to the beginning of the linked list, so head needs to be updated. You just need to create a new node, right? Head needs to be updated and this link needs to be actually preserved. So clearly adding an item to the head, to the beginning of the linked list is going to be done in constant. Also removing can be done in constant, because basically the thing that you need to do here in removing is updating the head to refer to the actually next items. So we have actually discussed this. Removing and adding to the beginning of the linked list can be done in constant. How about the other side? If you have access to the tail and you are removing, or for example, you are adding an item to the tail, again, the only thing that you need to do is just updating this reference and updating tail to refer to this reference, right? So adding an item to the tail can be done in constant, but unfortunately removing an item from the from the end of a linked list needs to be done in linear time if you have a single linked list. So you have to start from the beginning and find the node before the tail, and so tail, this reference needs to be updated to null, and tail needs to be updated to refer to the node exactly before the tail, the previous tail. So because of this, removing from the end of the linked list is going to be done in linear time. So now it's clear that which side is going to be considered as the front of the queue, which side is going to be considered as the rear of the queue. Because removing from the tail in the linked list is going to be linear, I wanted to avoid that. So removing from the front can be done in constant. So front is going to be the head and rear is going to be the tail. So now the implementation for linked list is going to be very simple. I have posted the source code for the queue, both the linked list and array based implementation on Blackboard. So just please download them and study the full implementation. The implementation of the linked list based queue is very simple. It is very similar to what we had in the linked list, but it's going to be actually much simpler. I have two references. Instead of calling them head and tail, it's just actually I've called them front and rear. Front is going to be exactly corresponding to head. Sorry for my handwriting, it's just terrible. Okay, this one is going to be head. I have written them. This one is corresponding head and this one is corresponding to tail. I've also keep track of the number of items as well, just like in the linked list. In the constructor, you just initialize front and rear to null and size to 0. The only three main methods that here I have is just enqueue, which is exactly like add last when we had access to the tail. The only difference here is that, okay, front is going to be head, rear is going to be tail. Everything else is exactly like the implementation that we discussed there. So it's just like add last in linked list, and dequeue is going to be exactly like remove first, that you are removing from the head. And if you actually just compare the implementation, you will see that they are exactly the same. Just the name of the references are different. So just a couple of things about the implementation. This is going to be a generic implementation. So this is based on, I have generalized it based on the type any type here. Of course, you need one class for the nodes, which is it can be exactly like the class that we have written, node class that we have written for the linked list. I don't need to change anything from there. What else? We are throwing an exception if someone called the dequeue over an empty queue, or for example, if you call a pick over an empty queue, again, you throw an exception. Pick is going to give you, it's not going to change anything from the content of the queue. It just actually tells you that what is at the front of the queue, what is going to be the next item which is accessible. So graphically, if I wanted to show you that what would happen if you create a queue which has been implemented using linked list, it would be something like this, that you have you create an object of queue, and then if you so basically front and rear at the beginning was null, but then if you called an enqueue, it's just like you create a node and you only have one node in your linked list. Both front and rear are going to refer to that. If you enqueue another item, the item will be added to the end of your linked list, right? So to the rear of your queue. So rear will be updated, the item will be added to the end. If you add another item, enqueue another item, again the item is going to be added to the rear, so it's just to the end of your linked list. Another enqueue, and if for example here you call a dequeue, this item needs to be returned and front needs to be updated. So this just shows you that what would happen in that case. Okay, so that was the implementation using linked list. Now I'm going to discuss the implementation of queue using array as the main data structure. Okay, so again, when I am actually using an array as the main data structure, I have to decide, you should think about it in this way, that you have an array. It's just like you're going to implement a list over that array, but you are not removing and giving access to remove and add from arbitrary position, but you just give the access to add the item from one side of the list, which is going to be, for example, if you have an array which is implementing a list, it's just like this is going to be the part that keeps the data as a list, right? One side of it is going to be front, the other side is going to be rear. So there's index 0 is going to be either front or rear, and the index n-1, if you have n item, the index n-1 is going to be the rear. Again, I'm emphasizing here that when I'm talking about two-sided in an array, I don't mean the last index of the array. I mean the last index that you have a data that you care about, the data that you have inserted. Okay, so which side is going to be front and which side is going to be rear? I need to just review the that table of the time complexity for the array and double check that which side is going to be better to be considered as front and which side is going to be better to be considered as rear. Exactly like the choice that we made over the linked list, right? So this table is actually telling me that if I remove or add from the beginning of the array from index 0, let me actually erase these parts here. If I add or remove from index 0, if I'm removing anything from index 0, I have to actually shift all of the items to the left, right? Or if, so in that case, if I choose front to be index 0, the time complexity is going to be linear. So that's not good. I try to avoid that. So now let's actually think about the other way. What if I consider rear to be index 0? So in that case, if I consider rear to be 0, let me actually just use a different color or blue. If I consider rear to refer to index 0, in this case, you are adding to the rear, right? When an item is going to be added, the item is going to be added to index 0. So again, here you need to shift the items because it is an array. You need to shift the items to the right. Okay, so unfortunately, when I'm using an array, one side, which is index 0, which is the beginning of the array, the cost for adding or removing from that side is going to be linear, and I can't do anything about that. So let me actually just show you, discuss that. Okay, we choose front as the index 0 and the rear as the index n-1, the end of the actual array. So, and we are going to try to, modify our implementation and see that is there, is it possible to modify this time complexity and get something better by just modifying our implementation or not. Okay, so if we choose front to be index 0, there are a couple of things that we should actually consider. First of all, I don't need a pointer for index 0. You always know where is the front. The front is, if you are going to fix it to index 0, so that's going to be index 0 and that's it. When you are adding an item to index 0, you have to actually shift if you the front is going to be index 0. When you are removing an item from index 0, I don't need to keep track of the index, the indicator front, because I always know this is going to be front. And the other thing is that I have to shift all the items to the left whenever I am actually removing. When you are adding to the queue, rear is going to be that index n-1, right? And rear is going to be implemented very efficiently because the only thing that you need in this case is that okay, for example, when you are enqueuing 6, 6 needs to be added here and rare will be updated, and there is no shifting here. So as far as you do have enough space, so enqueuing can be done in constant. So the issue that I need to work on is front. How can I modify my implementation to get rid of this shifting? Okay, I wanted to avoid shifting the items. So when you are removing the actually this item 4 from the queue, I don't want to shift. If I shift, this is going to be linear. So one thing that I can do here is that instead of always considering index 0 as front, I can define a pointer for front and say that, okay, when an item is going to be removed from the queue, instead of shifting and always say that the front is going to be stored as index 0, I will say, okay, remove an item and update the front. And so, okay, index 0 has been gone. This has been removed from the queue. Okay, so update the front and say that index 1 is going to be front now. So in this way, I have, got rid of the shifting, because I didn't fix the index 0 to be the front. Front now is moving. It was actually index 0, you removed an item, now front is index 1. If you remove another item, so if you call another DQ, front is going to be this index, right? So just like rare, which is moving over the indexes, front is also moving over the indexes. So always the part of the array, it's just like you have a window over the array which shows you which part of the this array is keeping the data. So for example, here this part is keeping the main data in the queue. You are not fixing it to some indexes. You are not fixing it from one side. So that's great. It actually helps me to implement both DQ and NQ in constant time. This one is kind of called the, we are not actually fixing, this is not a one-sided array anymore. It's just like you actually release that restriction, so your array is not one-sided anymore. So, but what is the issue that we can actually, face here is that think about your this case that you are going to have a fixed, for example, array, right? The size of the array is fixed, and you keep adding and removing from your queue. What would happen? At some point, it's just like rare will reach to the end of the array, right? What should I do in this case? There is nothing more here. So one action that you can do is just get a larger array, okay, and copy everything, just like what we did for the case of a stack or list, that whenever the array is full, you get a larger array and you copy all the items there and continue. So one thing that I can do is just like do that, and so continue from here, that this is going to be rare, this one is going to be front, and you continue. But what if you, you can see that there are plenty of spaces here that I'm not using them. And if I keep continuing and getting more and more space for my array, so you soon are going to run out of space, right? Because you are taking a lot of space and you don't really need it in most cases. Just think about it in this way, that you just, for example, 10 items are going to be in the queue at each point. So you frequently add an item and remove an item. So it's just like this window is moving. So this is not a good idea to expand the array whenever rare reach to the end of the queue. Rare reach to the end of the array. One thing that I can do is I would like to reuse the space that I have at the beginning of the array, right? So here the idea is that whenever rare reach to the end last index in the array, I can check and see that if there is enough space, reset rare, and the next enqueue is going to actually just put an item at index 0. Okay, if there is a space. If there is no space, of course, if you have already actually filled the whole array, you need to get more space. But if there is some space at the beginning of the array, I wanted to reuse it. So this idea is going to call circular array. Although array is going to be a sequential, has been stored in the memory in a sequential way, but the way that we worked with it and simulated, it's just like it is a circular array. So whenever you reach to the last index, the next accessible index is going to be index 0. So just like you are actually going around a circle. So how we can implement the circular array? One thing that you can do is that, okay, put some actually if-else conditions and say that, okay, whenever rare reach to the end, just update it and put it as 0. Not only rare, you have to do it for the front index as well. Okay, so you can see here, not only rare, you can actually at some point you might actually just go forward and front can actually reach to the index 0 as well. So for both rare and front, you have to put a couple of if-else conditions that, for example, if it reached to the last index, you have to reset it to index 0. Here I'm going to show you a technique which is very nice, and you can implement the circular array without actually using if-else statement and make your implementation very complicated. Remember, in programming, we have an operator which is called the modular operator, right? That we usually actually we show it in the context of high-level programming languages. Basically, in all programming languages that I know, the operator has been shown using percentage. Okay, so this is called the mod operator or modular operator, which is going to return the integer, the remainder of integer division. So, for example, if I got 8 mod 5, this is going to give you the remainder of dividing 8 by 5, which is going to be 3. If I actually divide 5 by 5, the remainder is going to be 0. If I divide 2 by 5, the remainder is going to be 2. So here the thing is that whenever the value is smaller than the items that you are dividing by, the integer number that you are dividing by, the remainder is going to be exactly the same as. So for example, 2 mod 5 is going to be 2. 1 mod 5 is going to be 1. Right? 0 mod 5 is going to be 0. So modular operator is going to have a very interesting properties for me, that when I am updating the indexes, for example, when you are updating here rare, you actually just say that, okay, when you are adding an item, you would think of it as updating rare as rare plus 1, right? But before actually after I add 1 to the rare, one thing that I can do is that instead of using an if condition, I can use the modulus operator. So rare plus 1 mod the size of the array is going to tell me, either if the index is going to be a valid index, it's going to return it. Otherwise, if the index is larger than the size, it will be reset to 0. Okay, so when rare reaches to the size of the array, it will automatically be reset. So I am going to use this modulus operator here. Okay, now not only that trick, I'm going to actually just show you another trick here as well. That instead of keep track of both pointers for front and rear, I can actually, in fact, only keep track of front and the number of items that I have in the queue. So front plus the number of items that you have in the queue is going to give you exactly the the pointer rear. So in the implementation, we are going to just get rid of rear. We are not explicitly keep rear, but whenever I needed to put an item in the queue, I need to put it as rear plus one. Okay, so that item is going to be front plus the size, the number of items in the queue, which is going to be count. Okay, so this index is going to be the next index that you have to put the item to add, and you have to when you are enqueuing an item, this is going to be the index that you need to put the item there. And one thing that I, instead of actually just checking that if it is greater than the size, okay, reset it or whatever, what I can do is that I can just implement it as using the modulus operator. Mod the size of the array, that we usually just write it as the max size, right? Max size was that static variable in our implementation of the list or a stack that shows the size of the array. So front plus count mod max is going to tell me where the next item needs to be inserted. That, for example, this time is going to be this one. Just think about it in this way that, okay, front was 7, okay? Just, for example, front was index 7 and count was 4. This was front. And this was count. So front plus count, this is going to be 11. Mod the size of the array, which is 10. This is going to give me index 1. So it actually just safely gives me the index that I need to put the item there. This is available in your if you check the enqueue, you will see that the enqueue has been implemented in the array-based implementation, as simple as just writing something like this, that items front plus count mod max size. And you actually put the item just at this index of the array. When you are removing an item, you need to actually put the keep this item somewhere to return, right? And then you need to update the front. How we are actually going to update the front in dequeuing? You are just adding 1 to front, and again, I get modulus over max size to just make sure that this is going to be a circular array, and the front will be reset whenever it actually reaches to the max size. Let me actually show it to you through some example here. It actually makes it much easier. In this case, the max size, the size of the array is going to be 6, right? So the max size is going to be 6. Just at the beginning, when you create a queue, front and count, both of them are going to be 0, right? And just now assume that you called the method enqueue. When you call the method enqueue, the value 6 needs to be inserted where at index front plus count mod max size. If you actually calculate that, this is going to give you the index 0. Front is 0, count is 0, add them and got the modulus over 6. This is going to give you 0, and so the item will be actually inserted here. The item will be inserted there, and count will be also updated. So count will be 1. This is something that actually happened after calling one enqueue. If you call another enqueue, okay, this time again calling enqueue 4, what would happen? You need to put 4 at index front plus count mod max size. This is going to be 0 plus 1 mod 6. This is going to be index 1. So the item 4 will be inserted at index 1 and count will be updated to 2. If you call another NQ, again, the same formula, front plus count, mod max size, this is going to be 0 plus 2 mod 6, this is going to be index 2. So 7 will be inserted at index 2 and count will be updated to 3. So now I have 3 items, front is at index 0, and this is the queue. I don't need to keep track of the rear because I know where is going to be the rear. If you call another NQ, again, front plus count, mod max size. So this is going to be 3 will be inserted at index 3 and count will be updated to 4. Okay, another NQ, I just wanted to show you that what would happen if we fill the array, or actually when we reach to the end of the array, not with or actually filling the array. If you insert 8, again the same formula, front plus count, 0 plus 4, this is going to be 4 mod 6, this is going to be index, the index 4, the item will be, the 8 will be inserted at index 4. Now, for example, let's actually just call a DQ. When you are calling a DQ, you know where is front. Front was at index 0, right? So you keep the value at index 0 to return it, and then front needs to be updated, right? Because it's just like 6 will be removed from the queue. How front is going to be updated? Front is going to be updated as front plus 1 mod max size. So 0 plus 1 mod 6 is going to be 1. So the new value of front is going to be 1. And count needs to be updated as well. So no, front is referring to index 1 and count tells me that, okay, I have only 5 items in the queue. So it's going to be, the rear is going to be here. Now, if someone, for example, let's just call another DQ here. If you call the DQ again, front, this item 4 will be actually returned and front will be updated as front plus 1 mod max size. This is going to be index 2 and count will be updated to 3 as well. So you have, this is going to be front and you are going to have only 3 items here. Okay, here let's just call an NQ. Let's see that what would happen if I call NQ. If you call NQ, you need to know that where to put the item, right? So we are NQing 9. Where we should put the item? Remember the formula was front plus count mod max size. Front is 2, count is 3, mod max size, which is 6, this is going to be 5, which is going to be exactly this index. So 9 will be inserted here, count will be updated as well. If I call another NQ, so you see that it's just like the end of the queue has reached to the end of the array. Let's see that what would happen in this case. So front was 2, right? 2 plus the count, which was 4, mod 6. This is going to be 6. 6 mod 6 is going to be 0. The remainder is 0, right? So the value will be inserted, the value 5 will be inserted at index 0, right? And count will be updated as well. So front is here and count will be updated to 5, and this is the situation of the queue. So you can continue, just play with this example, call the NQ and DQ and play with the formula and see that how it actually nicely simulate a circular array for you. I mean, using just simply these 2 formulas without putting, you know, a couple of if-else conditions to update the front end. And if you're keeping array rear as well. Okay, another thing which is important here about the queue, the array implementation of the queue, is what would happen if we we really don't have a space in the array. What if we really fill the whole array? Exactly like a stack and list, in that case, we would like to have a dynamic array. It means that we just, automatically get some space and expand the size of the array. In the implementation of list and stack, both of them, implementing the method expand was very simple. This is just, I put the implementation of the expand from the list or from a stack. Both of them was the same, actually, were the same. The only thing that you need was to get a larger array, right, of double size, and then copying all the items from the previous array to this new array and copy the reference as well, and that's it. But if I do the same for the queue, there is a good chance that you completely ruin the queue. So when the array is full, when you are actually implementing a queue, the array would look like this, okay? Front and rear, or here actually I showed it as back. You can see that they can be anywhere, right? Front, for example, can be here, and the rear or back can be here. If I just follow this implementation, the thing that would happen is that you started from index 0 and just copy all of the values corresponding based on the index, from index 0 to index 0, index 1 to index 1, and continue until the last index. Now, what would happen? You are going to have the new array like this, that all the items have been actually all the items have been stored here, and front and rear are actually just adjacent to each other, and the rest of the array, the space that I got from the memory is here, and this is going to completely ruin the implementation. In that case, you would actually rewrite the items and lose some of the items here. Okay, so one thing that I can do is that actually, when I'm getting more space, what I would like is something like this, that this part should be at the beginning of the new array, and this part should be at the end of the new array, right? So I wanted all the items to be copied in this way. This part needs to be copied here, and this part needs to be copied here. But writing a code like this is not hard. I can do it. But I'm going to show you a trick that simplify the implementation. Instead of copying all these items at the beginning of the array and these items at the end of the array, I can just think about it in this way, that anything that is at the front, I can actually just copy it at index 0, and just think about it in this way. So I would care about the items in this order, right? Starting the front until you actually go back until you reach to the rear or back. Okay, instead of copying this part to the end, I can start copying all of these items from index 0, and then after that I will copy these items at the end. Implementing this is going to be much easier, right? So I am actually going to have a loop that actually started from index 0 until it actually reaches to count. But what I am doing is that instead of copying from index I to index I in the new array, I will copy from this formula. I will copy front plus I mod max size. I will copy this actually index in the index I. So in this way, I will simulate this action that I will copy from the index front until I reach to the rear, or the end of the queue. Okay, and the rest of the implementation is going to be similar to the previous one. The only difference here is that I need to, after I have actually done the copying, front needs to be updated as well. Front is not going to be this index anymore. Front has been reset, not reset, front has been updated to index 0 because we copied the items in a different manner. At the end of this lecture, I would like to also cover an interesting application for the queue. One of the applications of the queue is in breadth-first search in graphs or breadth-first traversal in trees. So assume that you have a tree, a data structure, like a tree, like this example that I'm showing you here. A breadth-first traversal of a tree is going to be, an approach that you visit all the nodes in the tree, but you want them to be visited based on the distance from the root of your tree. The root is going to be A here, right? So in this way, the thing is, I wanted to visit all these nodes based on this order, that I wanted to visit A first, then I want to visit all the nodes at the closest distance from A, which is going to be B and H. And then I wanted to see the next set of nodes, which are the closest distance from the root, which are going to be C, D, G, and I. So it's just like a breadth-first traversal or level-by-level traversal. So this figure actually shows you that how I'm going to visit the items. First A, then B, then H. It's just like a level by level. Then C, D, G, I, and then E, F, J, and K. How we can implement such an algorithm? So here just assume that we are printing all these items in the output, and I want them to print them in the form of A, B, H, C, in this level, in this format. Just a level by level. One thing that I can do is just use a queue. This is going to make the implementation very simple and very efficient. In this way, I can visit all the nodes in just linear time. Let me actually show you the formula in this. Let me show you that how the algorithm works. So at the beginning, you create a queue. That queue is going to be empty. What you are going to do is that, in fact, when you have a tree, you only have access to the root item. So you push the root item or enqueue the root item to your queue. So A will be inside your queue. Then you need a loop that you actually continue in this way until there is anything in the queue, until the queue is not actually empty. What I am doing is that I just need to remove an item from the queue, which is going to be removed from the front of the queue, and visit all the children of this node. By visiting, and then you actually just push all of them into the queue, enqueue all of them to the queue. What would happen here is that A will be removed from the queue. Okay, A will be removed and A will be printed in the output. Then so let me actually just show it to you in this way, that I would create another queue. A will be removed, A will be printed, and then the children of A, which is going to be B and H, both of them will be actually pushed to the queue. Then the next action that you do is that, okay, it's just like you are in a loop. You again double check that if the queue is empty, which is not empty because there is B and H, there are B and H in the queue. So you remove something from the queue. So what would happen in this case? B will be removed. So it's just like the queue looks like this. B will be printed. And then remember, push enqueue the children of B to the queue. So C, D, and G, the children of B, will be pushed to the queue. You can see that by enqueuing the items to the queue C, D, and G, they will be pushed at the rear of the queue, right? So they will be pushed after H, and this is important for me. This is exactly something that helps me to implement the um, birth first traversal. The next action is that, okay, you double check if the queue is empty or not. The queue is not empty. You remove an item, you dequeue an item from the queue. What will be actually removed? H will be removed, right? H will be removed from the queue. You will print H, and then you will push all the children of H to the queue. So the children of H, there's only one child, so I. Now you can see that nicely I will be actually pushed to the queue, and it will be pushed at the end. Okay, again, you double check if the queue is empty or not, which is not empty. Okay, so you dequeue another item. So by dequeuing another item, C will be actually removed from the queue, right? And the children of C, C will be printed in the output, and the children of C will be pushed to the queue. There is no child for the C, so nothing will be pushed to the queue. So, and then again, you double check. If the queue is empty, you will stop, but the queue is not empty. So you remove another item from the queue. This one will be removed from the queue, and you see that I will not be, for example, removed. D will be removed. D will be removed from the queue. It will be printed, and then you would enqueue the children of D to the queue. And you can see that because this is the queue, nicely E and G will be pushed to the end of the queue. So the order of them will be completely preserved. The next item will be actually processed is going to be G. E and F will be, they will wait in the queue until until it's their turn. So you continue, just check the queue. If it is empty, you will stop. It is not empty, you will remove another item you dequeue another item from the queue. G will be removed, right? It will be printed, and then the children of G will be pushed. There is no child, so you don't actually push anything to the queue. And then you again double check the queue. If the queue is empty, you will stop, but the queue is not empty, you dequeue an item from the queue. This is going to be I, right? This one will be removed from the queue. You will print it in the output, and then you will push the children of I, which are J and K, to the queue. J and K will be pushed to the queue. Again, you double check the queue. If it is empty, you will stop. It's not empty, you will dequeue an item from that. So E will be popped, will be dequeued, E will be printed, the children of E will be pushed. There is no child for E, so nothing will be pushed to the queue. Again, you double check. If the queue is empty, you will stop. The queue is not empty, so you continue. F will be popped from the queue, right? It will be printed in the output, and its children will be pushed to the stack. There is no child here, so nothing will be pushed to the stack. You continue, double check that if the queue is empty, you will stop. The queue is not empty, so we call a dequeue. J will be removed from the queue. It will be printed. Its children will be pushed to the queue. There is no child, so we don't actually add anything to the queue here. We double check the queue is not empty yet, so you remove an item from the queue. This is going to be the last item actually, K. K will be printed in the output. It has been removed from the queue. And you push the children of K. It doesn't have any child, right? So you don't actually push anything. You again go and double check the queue. The queue is empty, you stop. And you can see that I actually got all the items in exactly the order that I wanted, in level by level order. This is going to give you a birth first traversal. I have all these examples that shows how the queue is working in this case.